Yeah, so first of all, I'd like to thank the organizer for the opportunity to speak and also for accommodating my constraints to speak over Zoom. And yeah, I'm pretty jealous of you guys that you can enjoy a good time at Paris. And I have to be here in California. But any case, so yeah, so I also want to thank everyone for staying a bit longer for this talk. So the talk today will be about QCD Wilson lines in IR chiral Lagrangians. And this is based on work in progress, but hopefully will be complete in this month or next month. And I would also like to point out a special thanks to Clay Cordovas and Scott Thomas. So this project is kind of have an interesting history. So it started almost like in 2023. So at that time, I had a nice conversation with Clay, but I probably Clay didn't remember anything now. But that sort of sparked some of the interest, and then I just went on and pushed it myself, and there was also interesting conversation with Scott Thomas that actually bring it into actual applications in real world. Okay, so this is where the project stands. Okay, so let me just tell you the setup first. So we'll be considering an ideal case, but then this will also be relevant for the real world. So we'll consider SU and QCD coupled to NF massless quarks. And in this case, there's a SU and F left symmetries and the SU and F right symmetries. And then there's also a U1 baryons. Okay. And at low energies, we'll work below the conformal windows. So at low energies, there will be the chiral symmetries will go through chiral symmetry breakings, and they will be broken down to the diagonal or the vectored SU and F. And in that case, the IR theory is basically described by the chiral Lagrangians. And this is nothing but a theory of Goldstone boson. So it's actually described by SU and F nonlinear sigma models. But importantly, there's Wess-Zumino terms. Okay, and these Wess-Zumino terms will also play a very prominent role in our discussions today. So let me just quickly recap how the Wess-Zumino terms is defined. So the Wess-Zumino terms is defined in a somewhat interesting way. So originally, this field that describe the nonlinear sigma models are living in a four-dimensional space. Okay, but then when we define this Wess-Zumino terms, we will extend this field into a five-dimensional space. Then we will write down the following Wess-Zumino terms, which is basically an integral of a sort of a topological terms in five dimensions. Okay, so it's given by a trace of u delta du to the power fifth, and then we integrate over M5. And importantly, this Wess-Zumino term has the following properties. So we want that this Wess-Zumino terms to be well defined in the sense that it only depends on the actual field configurations of M4 instead of how we extend to M5. So this is actually possible because if we look at the difference between two Wess-Zumino terms, let's say one extension to M5 and the other extensions to M5 prime, then the difference is basically evaluating the Wess-Zumino terms on a closed manifold. And this closed manifold is given by the unions of M5 times M5 prime. Technically speaking, it's minus M5 prime, okay? And when we evaluate this Wess-Zumino terms, what's nice is that this gives you exactly, it always gives you 2 pi I times integers. So that means that if we evaluate the Boltzmann weight, which is the exponentiations of the Wess-Zumino terms, they are invariant. Okay, so that's why this is a well-defined actions, or well-defined terms that can be added into the actions. And crucially, this term is also required to be there in order to match the anomalies. So we know that the SUN QCDs, the SUNF left has a self-anomalies and SUNF right has a self-anomalies. And their anomaly coefficients actually fixes are precisely n, which is the n that appears in SUN QCDs, and that precisely matches. This anomaly is precisely matches by the Wess-Zumino terms if we pick the coefficient n to be exactly n. Okay, and this n is also integers, so this guarantees that the West-Williams terms is well defined. So this is the first piece of things that comes from anomaly matchings that tells us that there must be a non-trivial West-Williams terms in the nonlinear sigma models. There's a second information that can be obtained also from anomalies. That is by noticing that the U1 baryons actually has a mixed anomalies with both the SUNF left and SUNF right. And in order to match that anomalies, that actually allows us to fix how the skyrmion, how the baryon current look like in a nonlinear sigma models. And this is basically given by what's called a skyrmion currents. Okay. Now, skyrmion occurrence is again kind of a topological terms, and this skyrmion occurrence actually tells you that baryons, if you think of baryons, which carries charge on the U1 baryon symmetries, they're realized as some interesting configurations in IR, which are called skyrmions. And these skyrmions are essentially some topological solitons in the nonlinear sigma models, and I'm going to say more about it later. Okay, so I'm going to say more about it later. So here, from this, you can already see that this is sort of a prototypical examples where using symmetries and topologies, we can understand a lot of interesting physics associated with the IR physics of QCDs. Oh, and also let me emphasize that the West-Williams terms is non-trivial because of you can think of it as that the pi 5, the first homotopy class to SUNF is actually non-trivial. Okay. Good. So this is the ideal scenarios that we're going to consider, the sort of ideal system we're going to consider. But I also would like to emphasize that even though this is sort of ideal scenarios, it's actually important that it's also good approximations of a real world QCDs. So a lot of things that I'm going to say in these systems can have applications to real world QCDs. So in particular, I want to emphasize one point, that is, if you think about real world QCDs, of course, we will take the gauge group to be SU3, where n equals to 3. But we know that there are 6 kind of quarks. There are the up, down, strange, charm, bottom, and top. But then, importantly, we want to divide them into 2 types. One is called light quarks, and the other is called heavy quarks. And roughly speaking, how we divide them is by comparing the mass of these quarks with lambda QCD. Okay. So lambda QCD is given by roughly 300 MeV. It's actually pretty, there's a large windows of lambda QCDs, but it's clear that the up and down quarks, it's much lighter than lambda QCDs. So we can think about our real world QCDs by treating up and down quarks as light quarks. Then we can think of them essentially as some massless quarks. Okay. But in some cases, we can also think of the strange quarks as part of the light quarks. So in that case, we can make NF equals to 3. But importantly, for the heavy quarks, because they're much, much heavier than lambda QCDs. So if we want to treat them in chiral Lagrangians, they don't appear as those massless quarks. Okay. So they, in fact, should be treated as some kind of Wilson lines. And I'm going to say more about it later. And also, I want to mention that, so we know that the strange quarks is actually much heavier compared to the up and down quarks. So if we want to do something a little bit more refined, we can add a sort of a mass terms into the chiral Lagrangians. So this M is a mass matrix, and then we can turn these things on in the chiral Lagrangians to make the chiral Lagrangians a better descriptions of these 3 light quarks. Okay. Good. So the talk today is basically about answering the following questions. So what does the Wilson lines, in UV QCDs flow to in the IR chiral Lagrangians? So this is questions to my best understanding. It's not addressed in the literatures. And in some sense, this is a question that should have been addressed almost decades ago. But as you will see that the answer to this question is kind of intricate, and it's well motivated, these questions, for several reasons. So when I started it, I was interested in this question because it is actually very interesting examples of renormalization group flow of line operators or defects. So there has been a lot of understandings about physics related to local operators. They create particles and they have non-trivial correlation functions. But line operators also play a very prominent role in quantum field theories. And Wilson lines is basically one of the first examples of line operators that will come into everyone's mind. And studying it in the QCD is a very natural thing to look at. So, and as we know very well, that QCD is a strongly coupled quantum field theories. So the algebraic flow is supposed to be interesting for various reasons. And second reason is that it's also related to what my comments before is that even though I'm considering an ideal case, it's actually a very good approximation of real-world QCD. And in this real-world QCD, if you want to describe a heavy quarks, a very natural way to describe them is describe them using some Wilson lines. So these Wilson lines are good proxy for heavy quarks. Okay, so this includes, for example, the charm, the bottoms, and the top. And the third reason why it's also interesting to understand Wilson lines in QCD is in some it's remotely.
I'm sorry, can I ask a question? Why?
Yes.
Why are you describing heavy quarks with Wilson lines? Usually, heavy quarks are described in some sort of non-relativistic way. Yeah. Heavy quark is not a gauge field. Wilson line is an integral gauge field. Maybe I don't understand what you call a Wilson line.
That's right. So when I say heavy quarks, I'm strictly talking about the world lines of the heavy quarks. So the world line of the heavy quarks will trace the Wilson lines.
It's not a Wilson line.
Sorry, I couldn't hear what you said.
This is not what we call a Wilson line.
Oh, that's right. I'm just thinking about some probe quarks, some probe quarks. The world line of a probe quarks will be Wilson lines, and then this will be approximations of a heavy quarks. That's what I'm saying.
Is it because the quark is not gauge invariant, so you need to attach a line to it, or is it set?
And that's correct. Yeah. I'm just saying that you can approximate heavy quarks like the world line of a probe quarks by Wilson lines. That's all I'm saying. Yeah.
Can you write a formula for Wilson line? What do you call it?
Yeah. So I'm just talking about the usual Wilson lines, like integrals of A, yeah, and then trace R. That's what I'm saying. Yeah. I'm just using it. Let's forget about the heavy quark things I'm talking about first. I just think of it as some probe particles for now. Okay, some probe particles.
Quark is a source of color field. This is not a source of color.
It's a delta function localized source along the world line of the quark. In the non-relativistic limit, when the quark is very heavy, its world line is fixed. You pick that world line is where you put the A. That's literally what the non-relativistic heavy quark theory is. It's the theory expanded about a Wilson line. It's completely standard. Okay.
Yeah. But I'm going to say a little bit more about the connection to heavy quarks later. Yeah. Okay. So the third motivation is somewhat remote. It's related to confinements in QCDs, and this is known to experts. But it's also, I guess everyone in the audience knows. But I just want to emphasize again. So the notion of confinements in QCD is different from pure Yang-Mills theories without matter, okay? And I would like to briefly review this. So in pure SUN Yang-Mills theories, in a modern point of view, we can characterize confinements using ZN-centered one-form symmetries. And this ZN-centered one-form symmetries will transforms the Wilson lines in the fundamental representations by ZN phase, okay? And we think about confinements as an unbroken phase of the ZN one-form symmetries, and the order parameters for this ZN one-form symmetries is the Wilson loops. And if the Wilson loops have area loss, then we characterize this as confinement. And one thing I would like to emphasize, which was also will be relevant for the talk today, is that if you think about Wilson lines, it actually has two perspectives of thinking about it. One is defect perspective, and the other is operator perspective. So when I talk about defects, I'm thinking about a Wilson lines that is oriented in the time directions. Okay. So if you cut at any arbitrary time slice, you always see the presence of Wilson lines as a source of color charge. So in some sense, the Wilson line give modifications to the Hamiltonians. Okay. And in particular, if the Wilson lines have area laws, then that means that if we look at the Wilson lines pointing up and the Wilson line pointing down, they're all oriented in the time directions. If we evaluate the expectation value of the Wilson loops, we can read off the potentials between these two probe quarks. And the potentials has to be linear in order to reproduce the area law. And this linear potentials is actually indications of the existence of a flux tube that stretch between the two probe quarks. Okay, so this is a defect perspective that we can think of this Wilson lines as some proxy of probe quarks. And there's also a different perspective, that is the operator perspective, where we insert the Wilson line at a fixed time slice and think of it as an operator that acts on the state. So in particular, we can start with the vacuums, and then we can act the Wilson line operator on the states, and this will create a flux tube. And this flux tube is essentially the states carried the Zn charge. Okay. So since the Zn one-form symmetry is unbroken, there should be some extended states that carries charge under these Zn one-form symmetries, which are precisely this flux tube. So this is the stories in pure SUN theories. But now in QCD, the first things to notice is that the symmetries that exist in pure Yang-Mills theories are actually explicitly broken by dynamical quarks. Okay. So we don't have the Zn one-form symmetry to talk about. And this is related to the fact that when we think about confinement in QCD, it is not characterized by Wilson loop. Okay. And a better way to think about confinement is that it's related to the fact that there are no asymptotic color charge states. Okay, so now let's talk about, let me also discuss the operator and defect perspective of Wilson lines in QCD. So in operator perspective, first things to notice is that since there are no Zn one-form symmetry anymore, so a flux tube state is not protected by any symmetry reasons. So a flux tube is not stable. Okay. And this is simply the fact that if you start with a flux tube state, you can just proliferate some quarks or pair create some quarks to break the flux tubes. To tiny little mesons. So these things, they're just like some tiny little mesons. Okay. So flux tubes would just decay into a bunch of mesons if there are light quarks in the stories. And this has a consequence that the potentials between two probe quarks actually is finite now. And so in particular, that means that the perimeter, the Wilson loop actually obeys a perimeter law. So say we again have putting two probe quarks. Okay. So naturally, one may thought that there's some flux tube that stretch between them. But if this flux tube is sufficiently long, then its energy preferred, then it's more economical to break the flux tube into using some quarks. Okay. So these are light quarks. Let me emphasize that these are light quarks. And so once, so basically the light quarks will come and screen the probe quarks and form some kind of heavy light hadrons. Okay. And so this is and in that sense, we can, if we bring these two probe quarks very, very far apart, the energy wouldn't grow with their distance. The energy would just stay finite because each individual systems, each individual Wilson lines just becomes a finite energy systems where it will combine with the light quarks to form some kind of heavy light hadrons. Okay. So that's why in this systems, the potentials becomes a constant, and the Wilson lines obey perimeter law. So since the Wilson lines obey perimeter law, so it's not a very good a way to characterize confinements. And a better way to think about confinements is to think of it related to some asymptotic color states. Okay. Good. So this is sort of the high level motivations. So now I would like to get into the real meat of the talk. So the first questions one should ask is that okay, so we're interested in understanding what happens to Wilson lines under renormalization group flow, but then the question is that whether this question would have interesting answers. So meaning that say if I have a Wilson lines, is it possible that it's just completely screened in the IR? So when I say screened, it just means that it flows to trivial identity lines. Okay. If it just flows to trivial identity lines, then there's nothing interesting to do with this Wilson lines. It's not interesting to even ask how to describe this Wilson lines in the chiral Lagrangians. But then the answer to these questions is that a Wilson lines, in fact, can never be screened in a QCD. Cannot be screened. Actually, let me say not completely screened. Okay. And the argument is actually very simple. So it's also typed with this ideas of defect anomalies. So the idea is that let's just look at what are the global symmetries of a QCD. Okay. So for simplicity, I'll just focus on vector symmetries that act on the left and right quarks in the same ways, just to make it simpler. You can do something more sophisticated, but I'm just do the minimum things. Okay. So naively, one would say that the symmetry that acts on both the left and right quarks is a U and F vector symmetries. And the way it acts is just basically rotating the flavor index of the left and right quarks by some U and F matrix. Okay. But this is not the correct answer. The reason is very simple, is that this symmetry is actually not faithful. It's not the faithfully acting symmetries. And the correct faithfully acting symmetries is actually a Zn quotient of the symmetries. And this Zn quotient is very important because the Zn quotient is there because this Zn symmetries is actually part of the SUN gauge symmetries. Okay. So this Zn symmetries, the way it acts is very simple. It's just basically rotating all of the left and right quarks by a root of nth root of unity. And if we rotate them by nth root of unities, you could have done this or undone this by taking the Zn center of the SUN gauge symmetries, which acts precisely in the same manner as this Zn part of the UNF symmetries. So that means that this UNF symmetries is actually counting more global symmetries than it should be. So the Zn part of the UNF is in fact a gauge symmetries. So that's why this is the correct global symmetries to talk about. In fact, this actually has a more lowbrow way to understand that. So the lowbrow way to think about it is that let's just normalize the baryon charge of a quark by 1 over n, okay? By b equals to 1 over n. And one thing to notice is that a single quark is actually not a local operator. When I say a quark, I mean the quark the Fermi operators associated with the quarks. It's not a gauge-invariant local operators. Okay, but if we only care about gauge-invariant local operators, then we'll notice that all the gauge-invariant local operators they actually have integer baryon charge. So in particular, consider, for example, the mesons. So the mesons is a combination of Q and Q bar. And they form representations that is the tensor products of the fundamental and anti-fundamental representations. And the baryon charge of mesons is, of course, 0. For a baryon, which is made of a number of quarks contracted by the epsilon tensors to make it gauge invariant. So a quark is actually in the representations that is tensor products of n fundamentals of UNF. And this one would have a baryon charge 1. Remember that I normalize a quark, the baryon charge of a quark by 1 over n. Okay. So here we see that all of the gauge invariant local operators has a baryon charge, integer baryon charge, while a quark, which is the one that transforms in a linear representations under UNF, actually has a fractional baryon charge. But they are not gauge invariant local operators. So with this correct identification of global symmetries, then we can notice the following fact. That is, the global symmetries, even though it acts on the all of the local operators, they form linear representations under the global symmetries. This global symmetry actually acts projectively in the Wilson line defect Hilbert space. Okay. So what I mean by that, so think about Wilson lines. States in the Wilson line defect Hilbert space are created, for example, by the Wilson lines that ends on a quark operators. Okay. We can also let it end on, for example, a quark operator to the power of n-1. So in all these cases, the states that live in this defect Hilbert space of Wilson lines will have baryon numbers given by will have a fractional baryon numbers given by 1 over n mod 1. Okay. And in particular, all the states, they actually form a linear representations under the group G tildes, which is the group that acts naturally on the quarks. But a linear representation of G tildes are generically projective representations of the quotient group G. So when I say projective representations, I just means that if we take products of two symmetry operators, there can be a non-trivial U1 phase that comes out. This is what I mean by projective representations. But now let's derive the following contradictions. So suppose this Wilson line is actually screened. So that means that it becomes a trivial identity lines. Then the endpoint of a Wilson lines is nothing but a local operators, right? The endpoints of a trivial lines is nothing but local operators. And this local operators, as we said, always has baryon number, which are integers. And also they form linear representations under G. So hence we derive the following contradictions, because in this case, we're starting with some projective representations, and projective representations are quantized. Okay, their projectivities are quantized. There's no way that it can flow into a linear representations under a global symmetries. So hence we derive contradictions. Okay. So this is this argument has also appears already in the literature. So when people were studying conformal defects, conformal line defects. So this is an example of what's called defect anomalies. Is there any questions about this argument or?
So are these phases known? Can you compute the phases?
Oh, you mean can we compute this phase?
Yes, the UV.
Yes, yeah, you can compute this phase. Yeah. So one you can essentially just take some U1 in this, okay, and then one thing to notice is that a U1, let's say a U1 in this, how should I say this? Let me just say that this phase you can compute it, and the way you think about it is says you think about the U1 embedded in this group and U1 embedded in this group. This U1 is actually smaller than this U1 by a factor of n. So the periodicity is smaller by a factor of n. So using that, you can actually derive this phase. Yeah.
Thanks.
Yeah.
So suppose we look at the adjoint Wilson line, so that the projectivity is trivialized. Do we know for certain that that one flows to the trivial line, or there's still some interesting dynamics to check there?
That's a very good question. So honestly, I don't know. Yeah. So in my stories, I was only focusing on fundamental Wilson lines to make it simple. But that's a good question. So
I think the analog question in QED is quite complicated, right? Like there's this paper by Sohar and Aharoni studying what happens to a Wilson line in QED, and for charge of order alpha inverse, it can be screened, but before that it cannot be, I think.
That's right. That's right. Yeah. So for adjoint QC for adjoint Wilson lines, there's nothing I can say. Yeah. Yeah. But there's some other arguments that actually I can talk about it later. Yeah. There's some other arguments that actually Zohar using a paper with Brendan, they can argue something that even for linear representations, there could be something non-trivial. So using some more intricate defect anomalies. Yeah. But I don't know whether it applies in this case. Okay, good. So now, as I hope that I convinced you that the answer to the questions, what happens to Wilson lines in chiral Lagrangians is supposed to be at least not trivial. But then, what is the correct answer? So I'll come up with the proposals, and the proposals to get into the proposals, the key is to go after symmetries. So the idea is that we want to go after the U1 baryon symmetries. Because what distinguishes the endpoints of Wilson lines and the local operators is essentially those endpoints of Wilson lines are quark operators, and they carry fractional baryon numbers. Okay, but one thing that's nice is that we actually know how the baryon symmetries are realized in chiral Lagrangians, and the way the baryon symmetries are realized in chiral Lagrangians are basically given by this skyrmion currents. Okay. And let me say a little bit more about skyrmions. So in chiral Lagrangians, baryons are realized as skyrmions. So skyrmions is basically some topological non-trivial configurations or some kind of topological solitons of the nonlinear sigma models. Okay, and there are some topological non-trivial configurations at a fixed time slice. So they can be, you can think of it as some kind of static particles once you find the solutions. And one thing that's important is that if you want this configurations to have finite energy, then you would demand that the field configurations at infinity, I'll work with polar coordinates, at infinity has to not depend on the theta and phi, which is the polar coordinate. Okay, there has to be a constant. Otherwise, your field U has a non-trivial variations at the infinities, and this will create some kind of kinetic terms, and that would blows up the energies of this kind of configurations. So you require this U to have finite energies at infinity. So as a result, even though U is a map from R3 to SUNF, you can effectively take it to be a map from S3 to SUNF. So hence, different configurations are characterized by the third homotopy group. And for large enough NF, this is just Z. Okay. Oh, this is, sorry, this is always Z. Sorry, I said something wrong. This is always Z. Okay. Good. So now, in fact, one can very easily construct this kind of soliton configurations. The way to do it is that we just take an SU2 blocks inside the SUNF, and then we just let this SU2 blocks, because SU2 is basically S3, so there's a very natural map from S3 to S3, which just map, sort of like wrap one of the S3 around the other S3 once. And this map is basically given by this. So you take orientation-dependent combinations of Pauli, and times non-trivial functions depends on the radius, okay? So we'll pick the convention that at infinity, f equals to 0. And at the origin, notice that at origin, because we want the configurations to be smooth, okay? So that actually put the non-trivial constraints on the possible values f can have at the origins. And this is always given by some integer times pi, okay? Otherwise, if this is not an integer times pi, then this skyrmion configurations will not be smooth at the origins. That if you approach it at different angles, it will give you different answers. Only if you take this f0 to be integer multiple of pi, then when you approach the origins, they get the same answers. So in this case, it's either +1 or -1, okay? So now if you evaluate the baryon number for these configurations, you will find the answer that is given by this, which is basically a functions of f0. And for this particular case, it's always given by n. So this n, which is the value of, controls the value of f0 at the origins, basically tells you this, the skyrmion numbers, okay? So this is how we think about baryons inside of chiral Lagrangians as some kind of non-trivial topological solitons of skyrmions. And now, let's talk about what happens to Wilson lines. So now we have Wilson lines, or let's say we think about Wilson lines as some defect oriented in the time directions. And then we can take some time slice, okay? So from the previous argument, we expect that on this time slice, we should see some kind of state that carries fractional baryon numbers. So in particular, baryon numbers has to be 1 over n plus some integers. So that means that we need to find some kind of, we know that this baryon numbers are essentially some skyrmion numbers in IR. So that means that we have to find some kind of fractional baryons. Fractional skyrmions in IR. Okay? But as we already said, that a skyrmion number is quantized to be integers. So how can we even find the fractional skyrmions? The key behind this is that we can allow ourselves to have singularities in the field configurations. So we consider singular, we allow ourselves to consider singular field configurations where the singularity sits at the place where the Wilson lines pierce the time slice, okay? So this is totally fine because this singular configurations, naively, we will say that, oh, it has infinite energy or infinite energy density localized at the origin where the Wilson lines pierces the time slice. But this is okay because we think of it as some kind of defects. So for defects, it's totally fine that there's some infinite energies sitting at the place where, or infinite energy density sitting at the place where the defect is located, okay? So this is actually, so the point I want to emphasize that this singular field configurations is not problematic. If we think about the Wilson lines, think about field configurations within the presence of the defects, okay? And since this field configurations can be singular, then that means that the values of f0 doesn't have to be integer multiple of pi anymore. So we allow this f0 to take some different values. And now with the idea that we want every state in this defect Hilbert space to carry the fractional baryon numbers, which is given by 1 over n plus some integers. So now we can try to come up with a way to force this to happen, okay? And the way we'll do it is that we want to think about the Wilson lines as some kind of boundary conditions. So we'll define the Wilson lines by boundary conditions of the sigma model field. There's some questions?
So can f0 be irrational multiple of pi, or does it always have to be
That's a very good question. It's not a rational multiple of pi. It's if you want a baryon number to be 1 over n, it's actually a non-trivial solutions to these equations.
Well, maybe the question was, can f0 be any number in the sigma model? Is it quantized in some units, even if that b comes out to be fractional, or is it allowed to be anything?
That's an absolutely good question, and I'm coming to that. If you give me one, this is basically the next question I'm getting to. That why cannot f0 take arbitrary values? And I can just give you the answer now, and then we can come back to it later. So the answer to it is actually very interesting. This only for b that is integer multiple of 1 over n. It has something to okay, only for this particular values of b, the fractional skyrmia that we see can have a well-defined Lorentz representations. So if you take any other values of f0 such that b is not properly quantized, not 1 over n quantized, then the fractional skyrmia you get doesn't have a well-defined Lorentz representations. Okay, and when I say well-defined Lorentz representations, that means that the skyrmias behave, the fractional skyrmias behave as bosons or fermions.
This is from some interplay with the statistics of the West-Amino term.
Exactly, that's right. That's right. Yeah.
And so you can only divide it. Okay, yeah.
That's correct. Yeah, yeah. I'll say a little bit more about that. Yeah. Okay. But I give you a spoiler already. So let me come back to say a little bit more about how we describe the fractional skyrmions. The Wilson lines. So the idea, the way we want to define this Wilson lines is that okay, we want to just carve out some kind of boundary conditions. We just sort of like cut a little tube around the Wilson lines. Okay. We cut a little tube around the Wilson lines, and then we just want to specify the boundary conditions of the field around this little tubes. So this is the way we can describe the operators, and this is actually very common. For example, this is how we describe various disorder operators. So disorder operators are operators that are not described by how they are not built up from the fundamental fields. Okay, so they're operators that are described by how the fields behave around these operators. So a classic example is the winding operators in compact bosons, but a more relevant example, which should have already appeared in the talk yesterday by Clay, that is how we describe Toff lines in gauge theories. So Toff lines cannot be written in terms of the fundamental fields. And the way we describe it is that we think of it as some lines where at the fixed time slice. Okay, so here I'm denoting this point as the points where the Toff lines pierces a fixed time slice. Okay, then around this time this points we can carve out a little sphere, a little ball. Okay, and then we basically specify the boundary condition that the integral of the field strength around this sphere has to be 2 pi. So this is the way we describe a Toff lines. Okay. So I just want to point out that the way we describe operators using boundary conditions is pretty natural. This is how we describe Toff lines. So now we will do similar things for this kind of Wilson lines. So there are 2 conditions it has to satisfy. The first condition is that it has to preserve the U1 baryon symmetries, so that whenever we measure the baryon numbers as different times, they should agree. Okay, they should give you the same answer. So in particular, that means that if we restrict the baryon currents to the boundaries, it has to give you 0. Okay, so this is the first condition. The second condition is actually a very intricate condition. So we want first of all, one thing to notice is that when we define this Toff lines, we only specify sort of conditions on these boundary conditions. So we want to do the similar things for the Wilson lines, but we want to do it in such a way that we are forcing that no matter we're forcing that when we evaluate any field configurations, find any field configurations here, they will have a fractional skyrmia numbers given by 1 over n plus some integers. Okay. So the way we do it is actually basically just saying that let's just take the field configurations around this S2, and then we extend this field configurations to some N3, some non-trivial N3. Okay, so we start with S2, we extend to some non-trivial N3. And then, but this N3, I want to emphasize, is not necessarily the same as this this particular time slice. Okay, it's just some arbitrary N3. And then we want that the integral of u delta du to the power 3, which is basically the skyrmion current, to give you always 1 over n mod 1. Okay? And this M3 has the property that its boundary is just the S2 that we start with. So this sounds like a very weird constraint from the perspective of the S2. But I want to emphasize that this conditions is actually independent of how we extend the fields, or independent of this N3. Okay? And the reason is very simple. Is because these things that that place the rows as skyrmion numbers, actually from the S2 perspective, is basically the Weismann-Witten terms of the non sigma model configurations on S2. And we know that for Weismann-Witten terms, it's just similar to the Weismann terms in 5D or in 4D, that it's actually independent of how we extend the field configurations. That if we evaluate the Weismann-Witten terms on a closed manifold, it's always integers. So that's why this conditions is well-defined, okay? So it's a very weird conditions, but it's actually well-defined conditions that only depends on the fields on S2, because we are taking these conditions mod 1, okay? So this is how we defined the Wilson lines in the chiral Lagrangians. And to be concrete, there's actually a very nice way we can think about the field configurations as a fixed time slice. What we do is that we just take the original skyrmion ansatz that we had here, and then we can just pick a particular f0 such that it solves the following equations that require that the skyrmion number is always 1 over n plus some integers. Okay, and notice that once you find one solution of this kind, let's say this solution is x, you can shift x by some n times pi, and this will again be a solution to these equations, and except that on the other side it will shift by some integer n. Okay, so this property will be important later. So basically the boundary conditions just fix the fractional values of f0 over pi. Okay, but there's something you can do a little bit more about this field configurations. You can actually allow to give some time dependence to these field configurations. You can, for example, add by some SU NF matrix in a conjugate way. Okay, so you can build some more general field configurations such that it satisfies the boundary conditions. Okay, good. So now as I come to actually a very important point that was raised before. That is, why is this f0 taking a very particular values? Why cannot f0 take arbitrary values? And the answer to this question is, as already anticipated, is that this is tied with the fact that the Weismann terms sort of quantizes, sort of make you fractional skyrmions, some into a fermions if this Baryons number is given by 1 over n. Okay. So first of all, one we ask is that how can we detect which Lorentz representations we are talking about, which Lorentz representation these skyrmions are formed. So the way to do that is that we can just take a skyrmion configurations and we can rotate it. If we rotate the skyrmion configurations by 2 pi, and if we get a phase, and if this phase is -1, then we say it's a fermion. If it's +1, then we say it's a boson. If we get some random phase, then this just doesn't have well-defined Lorentz representations. Okay, and the way we can rotate the skyrmion is very simple. We can just apply this an SUNF transformations to the static skyrmion configurations of this type. And if we do it, it will just rotate the skyrmions by some angles, which is controlled by this t. Okay, so if we can consider a few configurations where t start with 0, and then we increase t to be 2 pi, then this will generate the 2 pi rotations. Okay, so now with these configurations, let me first review how we think about smooth skyrmions. Okay, so for smooth skyrmions, we can consider the following extensions of the field configurations. So we will start with, we'll basically extend the U0, the skyrmion ansatz, into the extra dimensions. Okay, and then we also remember that there are some conjugated actions that rotate in these skyrmions. Okay, so this is how we're going to extend the field configurations. And let me first consider a case where this describes smooth skyrmions. So in this case, the Westerno-Witten terms is actually very nice. It's actually a total derivative. So it you can make it again into integrals in 4 dimensions. And this, roughly speaking, takes the following form. So one thing I want to emphasize is that you see in these expressions, what crucially appears is basically something that is like that's something that appears in a skyrmion currents. Okay, so that's why it's not surprising that if you evaluate it for the skyrmion configurations, it's basically a terms that only depends on the skyrmion numbers, okay, or the baryon numbers in this case, and the expressions takes the following form. So now if you plug in an AT, which interpolates from t equals to 0 to t equals to 2 pi, you will find that there's a non-trivial phase that's generated because of precisely this Westerno-Witten terms. So when you do the 2 pi rotations, you get a non-trivial phase, and this phase is nothing but -1 to the n times b. And this is very nice because when b equals to 1, which is basically a baryons, then we see that this baryons is a fermion if n is odd, because we get a -1 phase by doing 2 pi rotations, and it's a boson if n is even. Okay, so this matches precisely with the fact that baryons is made of a number of quarks, and so when n is even, it's a bosons, and when n is odd, it's a fermions. So this is a calculation that has been done in the 70s by Witten, but now we are going to generalize it to the fractional skyrmion case. But one thing to notice is that because we are considering the fractional skyrmions as some kind of configurations with singularities, okay? So, or configurations with non-trivial boundary conditions. So we need to deal with, we actually need to talk about how to write down Westerno terms in the presence of boundaries. So when we start with the configurations in 4 dimensions that has boundaries, we will naturally has to extend these boundaries also in 5 dimensions, okay? So when we extend it into 5 dimensions, this boundary will become a 4-dimensional boundaries in my 5 dimensions. Okay. And what we do is that we'll basically put on this 4-dimensional boundaries a boundary Westerno-Witten terms, which is nothing but the expression that I already wrote down. Okay. So this will guarantee a nice variation principles. And it will also guarantee that it will not depend on how we extend the field configurations. Okay. Okay, so this is what we would put on these boundaries. And let me emphasize that the boundaries of these boundaries is essentially the bound is essentially S2 times R, which is a tube around the Wilson lines. So now you can again do the 2 pi rotations. And then we will now also get a phase from the combinations of the Westerno terms and the boundary Westerno terms. And this phase is nothing but, again, -1 to the n times b. But now this is important because only if b is an integer multiple of 1 over n, we can get -1 or +1. Otherwise, we don't get the well-defined, we don't otherwise we just get some arbitrary phase, okay? So that means that only for this very particular values of f0 such that b's are quantized, well, we can guarantee to get a proper Lorentz representations. And in the special case, when the baryon number is equals to 1 over n, this phase is just -1, which is nothing but producing the fact that quark is a fermion. Okay. Good. So, is there any questions at this point? Okay, if not, I'm going to discuss applications of this to heavy light hadrons now. So yeah, so when I say this project, this is kind of an academic questions that is a conceptual question that's interesting to answers. But it's actually interesting that you can actually produce a number that compare with actual experiments. Okay, so the idea is that we want to think about this baryons, this Wilson lines as some source of some coming from some heavy quarks, and when we put in the heavy quarks, it will attract a light quarks to form a gauge invariant states or gauge invariant particles. So, for example, it can attract a single light quarks to form a heavy light mesons. So this, for example, can be thought of as the B0 or B plus. So we can think of this Wilson lines as a proxy of a bottom quark, and then it will just combine with a light quarks, either up quarks or down quarks. Okay. Or it can combine with Q to the power n-1 number of light quarks to form some kind of heavy light baryons. So in real world case, we have a bottom quarks. It will combine with some let's say two up quarks to form some sigma particles, or an up and down quarks to form some lambda particles. Okay. So here I wrote down their mass and also the mass difference between them. And one thing I want to emphasize is that the mass difference is something that actually can be computed using the chiral Lagrangians. Because we should think about that, you think about this particles as they will get infinite energies coming from the Wilson lines or coming from the heavy quarks, but you will also get some additional contributions coming from the light quarks. And the mass difference of this heavy light mesons and heavy light baryons is a number that can be reproduced by the chiral Lagrangians. And in particular, I'm going to reproduce it using what's called SU2 skyrmion models. Okay. So what is the SU2 skyrmion model? So it's a nonlinear sigma models, which first has the actually, I think I already written it down, so I'll just go down here. So the skyrmion models has two kinds of terms. So it has two derivative terms and also four derivative terms. And the four derivative terms is actually important because if you just have a two derivative terms, the skyrmion would prefer to shrink so that it will minimize its energy. Okay. So if you just have a two derivative terms, it will shrink the skyrmions. So it's not a stable configurations. But if you have a four derivative terms, it will prefer to expand the skyrmions. And with these terms, you can actually stabilize the skyrmion configurations. Okay.
Isn't there another four derivative term? There are at least two, right?
There's let me think.
There are like two different like flavor traces.
Oh, you mean actually that's a good point. Yeah.
And not just the chiral Lagrangian because of that, right? Because you're just adding one particular.
Yeah, that's a good question. So let me think about it a little bit more. So I quote this Lagrangians from the paper by Napi and Witten. So in there, this is the only four derivative terms they wrote. Yeah, I suspect maybe the other terms can be redefined into these terms, but I'm not sure. Let me don't.
Yeah.
Okay.
We can discuss.
Yeah, we can discuss it later. Yeah, but let me just get to the punchline. Good. So one thing I want to emphasize is that now if you plug in the skyrmion configurations, you get the energy density, and the total energy is given by this. And you see that in these expressions, everything is finite in r equals to 0, okay? Except this term. This term blows up at r equals to 0. So this is a divergent terms. I remember that when I fix the boundary conditions, I already fixed the solution F0 mod pi, okay? So F0 mod pi is always fixed. So that means that the divergence that appears here is always the same for the same boundary conditions, okay? So they give you the same divergence. So that's why if you compute the two skyrmions of different baryon numbers, but with the same boundary conditions, their energy difference is some finite numbers. And that is the numbers that presumably can be compared with a actual mass gap. Okay. And so this is what I've done here. So we can consider a meson configurations where it will just attract a single light quarks. So that means that we want to find the solutions to these equations with 1/3 on the right-hand side. So the light quarks carries 1/3 of the baryon numbers, and we find some some F0s. And for baryons, it will have 2 light quarks. So that's why we want to find the solutions to these equations. And then this is a solution that we found. So this is what happens if we solve the differential equations that minimize the energies. And so let me just give you the configurations. So for this one, this is what describe a smooth baryons. Okay. So and as you see that at origin, it goes to basically pi. So this is supposed to describe a protons or neutrons. And this is what describe B mesons, where at this point it's approach 1.3. And this is what describe B baryons, so which approach minus 1.84. So it's somewhat interesting that in this case it will just decay directly, but in this case it actually prefer to sort of bump up a little bit and come down. Okay, I don't know why. It's just coming out of the numerics. And now, if we put in input the proton mass, we can actually compute the mass difference between this B mesons and B baryons, which is roughly somewhere around 550 MeV. So if you compare it with the mass gap, yeah, it's in the ballpark is similar. But strictly speaking, I think we should compare it with this one, not this one. So it's still quite kind of a bit off because I'm evaluating the lightest configurations in the heavy light baryons. Okay, but anyways, this is a number that produced from the numerics, and it seems to, at least roughly speaking, agrees.
But what's the logic here? You use the proton to fix the rho, the coupling of the term.
That's right. So in this case, the proton mass allows you to fix the ratio of F pi. I don't remember the precise combination. I think it's ratio of F pi and E. I think you can fix this. And the mass difference also only depends on that ratios. So that's why you can produce this mass difference.
But,
Yeah.
but even before you go to compute this schema, I don't know, what do people think about this experiments? I mean, there are many other things you can compute.
That's right. So yeah, so what people have done.
Using chiral Lagrangian, you find scattering. Are you now going to tell me that I can compute also find proton scattering because there are experiments? It seems like a very tall order.
Yeah, so there's actually attempts that people start with use some skyrmions as protons, and then expand the chiral Lagrangians around that backgrounds, and then you can compute some meson scatter of protons, like very sort of but these models are not very, very good. They are sort of like, for example, in the Napi and Witten papers, they use they compute some I think magnetic moments and some other things, and they compare with experiments. It's like within 30% of accuracy. It's not like right at the spots, but the ballpark is roughly the same. Yeah.
But what went wrong? Because we started by saying, well, we know exactly how the baryon current looks, symmetry matching, and now suddenly we find that something doesn't work, within 30%. Why
Yes, so
is it going to work precisely?
Yeah, that's a good question. So I think so. First of all, the models I think becomes better in the large n. When n has become larger and larger, it's better. And the second thing is that there are higher derivative terms, and I think the higher derivative terms will probably contaminate. So we only truncate at this orders. So if you start putting more higher derivative terms, I think that would probably improve the result.
I think as Julio was saying before, there are even more terms in the same derivative. Yeah.
That's right. Yeah, that's right. Yeah. I need to think a little bit more about the other terms. Yeah, but
Correct. I Yes, in the case of fine scattering, you say, okay, it's Fy over lambda QCD. And here, you can add as many terms as you want, but if they are all of the same order at the scale of the experiment radius, then they'll never going to work. I mean, there's no parametric. Is there some parametric expansion parameter which is going to improve things in what terms?
Yeah, I think if you work in large N, like when I say large N is large SUN,
Yeah.
then this model is supposed to be better. That's my understanding. Yeah. But unfortunately, our N is 3. That's yeah.
How about, before you go into this calculation, you predict that everything should work the same for no matter what the heavy meson effect. We replace D by C and it should do the same.
That's also a good question. So yeah, so so I was talking before. I was just talking about the calculation related to protons. In my calculations, there's also effects strictly speaking, there should be some effects coming from also the heavy quarks. Like for example, for if you compare it with if you replace the bottoms by char, these numbers will also be shifted, and so this heavy quarks actually does affect the actual mass gap. Yeah. So what I did here is sort of approximations.
Why shift it?
Sorry.
Why shouldn't it shift it according to what your point does? Should be the same?
Because those quarks mass, they are not strictly infinite, right? There are still like some finite numbers, and yeah, they will actually still have interesting interactions with the light quarks. Yeah. So what I hear is really assuming that the heavy quarks is infinite energies. And some kind of probe there. Yeah.
By the way, just for the record, I think there are 10 dimension 6 operator, or like the four derivative term for the same dimension. Like 8, and there's 2 double trace and a single trace, and then there's 7. Then put the mass of the electrons, and feed it both. I think on the lattice, few of them, and to the experiment. So in principle, you could just take the actual kind of Lagrangian and repeat this, and let's see.
Yeah.
Just keeping the leading large gap. I mean, that's where the problem is.
Yeah, then that maybe this is single trace. Yeah, so this is the single trace operator. Yeah. So okay.
That's good. Yeah. Oh, sorry. Are you saying that this is the only single trace, or there's another single trace that appeared?
I think this is the only single trace. And this four derivative term.
Well, yeah, it's the only single trace that you have no mass.
Yeah, if you have mass, there's more stuff. But without mass, there's a single trace operator.
Yeah, good. Yeah, so I think that's also another answer to Slava's questions. Yeah, that's right. So this model, yeah, this is there are more terms that should be added if we just take a finite n. Yeah. Good. Anyways, yeah. So yeah, I think I already get minus 7 minutes. But yeah, so let me just conclude. And yeah, so we describe a disorder operator realization of the Wilson lines in chiral Lagrangians, and we match the correct quantum numbers, and we also estimate the mass gap. It's not perfect. It's but the number is sort of at least had the right order of magnitude. Okay. Yeah, so what I didn't discuss is that if you have dysfunctional fermions, you can also kind of Wick rotate it and then use it as some proxy of describing how a flux tube is dissolved into pions. Okay, so let me just stop here. Yeah, thanks. Yeah.
Maybe related to that last comment. So there's also some complicated operators, which is the kind of would be one from symmetry generator, which is not topological in QCD.
No, you mean are you asking whether there are some one from symmetry generators in this
No, I'm saying, in addition to the Wilson lines, the UV, there's the integral of F, right? That's the Cook-Whitman like surface operator. Which presumably also should tell you something about the flux tube breaking into quarks. Do you know if this was something trivial or?
Sorry, I didn't follow what you said. You said integral of F. You're saying that one from symmetry in QCD or?
He's just talking about the surface operator. It's not topological, but there's some UV surface operator that's an integral of f.
Yeah.
You could try to track that, just like you tried to track the line.
Oh, I see. Sorry, I didn't hear what you said. Okay, that's interesting. I think that probably at the end will boil down to the same analysis here. I feel like, yeah, because that thing should.
But it doesn't end on a baryon or on a quark. So I don't know if it can end or.
Oh, yeah, I see what you're saying. You just okay. Yeah, I think that's an interesting question. Yeah. You're just asking what happens to that operators in IR, right? How to describe that operators as a chiral in the chiral Lagrangians. Yeah. So okay, so yeah, that's an interesting question. Yeah, that's right. Yeah, I don't have anything to say. Yeah, but yeah. That's right.
So can I ask you? So there is another effective theory produced for heavy quarks. It's known as heavy quark effective theory. So can you compare like your approach with it, like how do the two compare? Can you compute things that cannot compute? Can you
Yeah, that's a good question. That's something I also I'm aware of, and I'm still learning a little bit about heavy quark effective field theory. I'll appreciate any feedbacks. I don't want to make any strong comments, but my rough understanding is that this mass wasn't computed using heavy quark effective field theory. Because my understanding of heavy quark effective field theory is that you think about the heavy quarks as almost massive, like has almost the same mass. Then you get some emergent symmetries for this that rotates this heavy quarks. Then you can compute the mass splitting between heavy light mesons of different type of heavy quarks. So that's my understanding. So for example, using heavy quark effective field theories, you can compute the mass difference between this and this, like and a charm meson, like B meson and charm meson. So that's my understanding, but I could be wrong. Yeah, I'm still learning heavy quark effective field theory. Yeah.
It's an EFT which is sort of in between, in the sense that you have only integrated the quark and not the anti-quark. And when you're all the way from the chiral Lagrangian, you integrate out both of the heavy ones. So you have this infinitely massive growth. So I think you just keep the particle instead of the anti-particle. So maybe there's also some matching.
I see. Yeah. That's something I would like to understand more. Yeah. That's right.
Questions?
In the business of, we didn't have time, but in this business of organization and flux to
Yes.
position solution, say, clients, that is basically based on, most of it is based on some rule. So can you go putting some order into what usually people do, and then you want parallel generators. You need some field models, all those kind of. You have some nice theory there, which you can sometimes show us.
Okay. So I couldn't hear the whole thing. So you're asking about the flux tube, right?
You can say.
Yeah. So but I think this is maybe a little bit of a stretch, but the rough idea is that now we can describe the Wilson lines. Okay. Then we basically just quick rotate the Wilson line. But we'll also work with just these models for now. So we just quick rotate the Wilson lines, and then we solve the differential equations that govern. We basically solve these differential equations. So this Wilson lines will define some boundary conditions, and then this will be a proxy of a confining string, and then we'll just see how this pion, this nonlinear sigma model fields evolve. So that's what I'm saying. Yeah. So I think something one could potentially compute is I'm not saying anything super useful. Yeah, I think something maybe one can compute is the interaction between mesons and the confining strings. But
But do you see the translation variance based those line direction somehow gets broken? Because
no. In this case, no. Yeah. So it's the translation invariance along the Wilson line is always preserved in this case. Yeah. So it's a little bit different from a picture that I had here. Yeah. Yeah, so that's a very crude proxy of this confining string dissolutions.
Questions? Let's thank Tat again.
Thanks, yeah. Thanks everyone.